folks, welcome back to the 9.4 video series. Again, we're talking about mathematical induction and using that to prove certain statements. So in this video, we're going to take a look at example number 2, where we will use mathematical induction to prove that 1 squared plus 3 squared plus 5 squared plus ... all the way to 2n minus 1 squared equals n times 2n minus 1 times 2n plus 1 over 3. Okay? And so, again, we're going to start with our basis step, where we show that this is true for p sub 1. All right? So, that means that I'm going to take the first term, 1 squared, and I'm going to see if that equals when I plug in 1 to the other side of the equation. So 1 times 2 times 1 minus 1 times 2 times 1 plus 1 over 3. So 1 squared is 1. All right, I get 1 times 3 over 3. And those reduce, so I get 1 equals 1. And I've shown that the basis step is true. Now, let's think about how we can solve for, show that the inductive step is true. So for the inductive step, we want to assume that it's true for p sub k, and then we want to show that it's true for p sub k plus 1. So we're going to assume that 1 squared plus 3 squared plus ... plus 2k minus 1 squared is equal to k times 2k minus 1 times 2k plus 1 over 3. All right, so we want to assume that's true, and we're going to use that to prove that 1 squared plus 3 squared plus ... plus 2k minus 1 squared plus the next term, which will be 2 times k plus 1 minus 1 squared. Okay, so everywhere there was a k, I put k plus 1, all right? And I want to show that same thing on the other side. Everywhere I see a k, I'm going to plug in a k plus 1. So k plus 1 times 2 times k plus 1 minus 1 times 2 times k plus 1 plus 1 over 3. All right. I think I'm going to need more room, so let me go ahead and bring that down here so I can work all the way across, okay? Now, very similar to last time, we're going to be able to substitute. So everywhere I see this, I can replace it with k times 2k minus 1 times 2k plus 1 over 3. That means all of this gets replaced with the things circled in the orange. So I'm going to get k times 2k minus 1 times 2k plus 1 over 3 plus, let's go ahead and clean up the inside here, but I don't want to FOIL yet, okay? So when I simplify that, it's going to give me 2k plus 2 minus 1 gives me plus 1 squared. And I want to show that equal to k plus 1 times 2k minus plus 1 times 2k plus 3, if I simplify those, over 3. Okay, so I noticed that the side that I want to make it equal to has a denominator of 3. So I'm going to try and make the left-hand side have a denominator of 3. So I get k times 2k minus 1 times 2k plus 1 over 3 plus 3 2k plus 1 squared over 3. And I hope that that's going to equal k plus 1 times 2k plus 1 times 2k plus 3 over 3. Okay, so let's add our numerators, okay? And at the same time, I notice that there is actually a common factor. So there's a 2k plus 1 here, and there's a 2k plus 1 here. So I'm going to go ahead and factor out that 2k plus 1. So I've got 2k plus 1, okay? And let's see what's left. Well, for the first term, I have k times 2k minus 1 left. And for the second term, I have a 3 and 1 of these left. So plus 3 times 2k plus 1. And I hope that equals k plus 1 times 2k plus 1 times 2k plus 3 over 3. All right, well, let's distribute in here, see what we get. So 2k plus 1 times 2k squared minus k plus 6k plus 3 all over 3. I hope that equals k plus 1 times 2k plus 1 times 2k plus 3 over 3. Ooh, getting close to the end of the page here. All right, so these two combine to make 5k, a plus 5k. So really I have 2k squared plus 5k plus 3, and that I can factor. So when I factor the 2k squared plus 5k plus 3, I get 2k and k, and then plus 3 and plus 1 over 3 equals k plus 1 times 2k plus 1 times 2k plus 3 over 3. And I look and I see that the numerators are the same and the denominator is the same. So I have shown using mathematical induction that, let's zoom back in, that if I add up the squares of every odd number, I will get n times 2n minus 1 times 2n plus 1 over 3, okay? So don't forget the basis step, don't forget your assumption, and then the work is really in the proof, but the basis and the assumption help us conceptually get there. All right, so we're going to end this video here. Come on back for the third video where we go through one last example of mathematical induction.